Welcome to this lecture about the mathematical details behind the principal component analysis. In the previous video, we covered the basics of PCA. In this video, we'll see how we can perform a PCA analysis by using simple linear algebra in order to understand the math behind PCA. I will here show the math based on the eigendecomposition of the covariance matrix. However, note that there are other methods, such as the singular value decomposition to compute the PCA, which will not be discussed here. To explain how the PCA works, we will use the following example data. We'll use PCA to combine the two blood pressure variables into just one variable based on data from 6 individuals. For example, person number 1 has a diastolic blood pressure of 78 and a systolic blood pressure of 126. Whereas person number 2 has a diastolic blood pressure of 80 and a systolic blood pressure of 128, and so on. For this dataset, it seems to be a strong positive correlation between the two variables. To compute a PCA, we can perform the following steps, where we first center our data. Then we calculate the covariance matrix on our centered data. Next, we compute the eigenvalues and eigenvectors of the covariance matrix. Finally, we order the eigenvectors and calculate the principal components, which is our combined or transformed dataset. Usually, one starts to center or standardize the data in the first step of the PCA analysis. In this case, we will only center the data, which means that we subtract all the values of each variable by its corresponding mean. We therefore subtract the mean systolic blood pressure from the individual observations. Centering the systolic blood pressure results in the following values, which tell how far away the original values are from the mean. We then do the same calculations for the diastolic blood pressure, which has a mean value of 82. We can summarize the centered data in the following table. When we center the data, it means that we center the data points around the origin. Centering the data around the origin will help us later when we rotate the data. After we have centered the data, we'll have the following values, which can be plotted like this, where the x-axis now represents the centered systolic blood pressure, whereas the y-axis represents the centered diastolic blood pressure. Next, we calculate the covariance matrix based on the centered data. Note that we have got the same values in the covariance matrix if we instead would have used the original data, since the variance does not change when we center the data. Remember that the main diagonal of the covariance matrix includes the variance of each variable. The sample variance of the centered systolic blood pressure is calculated like this. When we calculate the variance of the centered data, the calculations become a bit simpler since the mean of the centered data is always equal to 0. To calculate the sample variance of the centered data, we therefore simply sum the squared values and divide by the sample size minus 1. Then we calculate the variance of the diastolic blood pressure by using the same equation. Finally, we calculate the covariance, which is a measure of how much the two variables spread together. The sample covariance is calculated by multiplying the centered values of the two variables. For example, we multiply the centered values for person number 1 and add that to the product of the centered values for person number 2 and so on. Finally, we divide the sum of the products by the sample size minus 1. We see that the spread in the diastolic blood pressure is a bit higher compared to the spread in the systolic blood pressure. The covariance is somewhere between these two values. Next, we calculate the eigenvalues of the covariance matrix. For more details, watch the lecture about eigenvalues and eigenvectors. We substitute A by the covariance matrix, and this term by lambda times the identity matrix, which has the same number of rows and columns as the covariance matrix. Subtracting these two matrices results in the following matrix. Next, we calculate the determinant of this matrix, which is the product of this diagonal minus the product of this diagonal. After some simplifications, we have the following quadratic equation. Quadratic equations like this can be solved in different ways, which will not be discussed here. However, if we plot how the left-hand side changes as a function of different values of lambda, we see that the left-hand side is equal to 0 when lambda is equal to either about 0.32 or 12.08. This means that if we set lambda to either 0.32 or 12.08, the left-hand side of this equation will become equal to 0 or close to 0 due to rounding effects in this example. These two values represent our eigenvalues of the covariance matrix. Next, we calculate the corresponding eigenvectors to these two eigenvalues. We'll start by calculating the eigenvector of the covariance matrix with the corresponding eigenvalue 12.08. To calculate the eigenvectors of the covariance matrix, we use the following equation that we have discussed in the previous video about eigenvectors. We plug in the covariance matrix and one of the two eigenvalues. If we multiply the covariance matrix by this column vector and multiply the eigenvalue by the same vector, we'll get the following system of equations. We now move these two terms to the right-hand side. After some simplifications, we have the following system of equations. Solving for y in the two equations results in that y is equal to 1.37x. For example, if we set x equal to 1, y is equal to 1.37. This vector is therefore an eigenvector of the covariance matrix. We can illustrate this vector in the plot like this, by drawing an arrow from the origin to the coordinates 1 and 1.37. We'll now normalize this vector to unit length, which means that it should have a length of 1. Watch the lecture about the eigenvectors and eigenvalues to see how one can normalize the eigenvector to unit length. After normalization, this vector represents one out of two eigenvectors of the covariance matrix. To find the second eigenvector, we do the same calculations as before based on the second eigenvalue. After some calculations, this vector represents our second eigenvector with unit length. Since the covariance matrix is a symmetric matrix, the eigenvectors will be orthogonal, which means that the angle between them is 90 degrees. Next, we order the eigenvectors based on their corresponding eigenvalues, where the eigenvector with the largest eigenvalue becomes our first eigenvector. Since this eigenvector has the largest eigenvalue, it will represent our first eigenvector. We therefore rename this vector so that it is called v1 instead of v2. Let's put these two eigenvectors together into a matrix that we called V, where the first column represents the first eigenvector with the highest eigenvalue, and the second column represents our second eigenvector. We'll now use this matrix to transform our original centered data so that the two variables are completely uncorrelated. We define a matrix D, which includes our centered data. Next, we multiply our data matrix D by matrix V, which includes our eigenvectors as columns. Then we get the new matrix with the transformed data. This transformed data is called principal component scores, or just scores, which represent the original centered data in the principal component space. When we go from our original data matrix to the transformed data, this can be seen like we rotate the data clockwise until the two eigenvectors point in the same direction as the x and y axis of the plot. The rotated data now looks like this. Note that the labels of the axes have now been changed to principal component 1 and 2. Let's call the two columns of the transformed data PC1 and PC2. If we plot this data, where we label the x-axis as PC1 and the y-axis as PC2, we will get the following plot, which represents the original plot after the rotation. Since we plot the principal component scores, this kind of plot is called a score plot. Let's compare the centered data with the transformed data. The variance of the systolic blood pressure is 4.4, whereas the variance of the diastolic blood pressure is 8. This is the covariance matrix of the data. We see that the covariance is 5.6, which tells us that there is a positive correlation between the two variables. When you transform the data using PCA, the first variable, called PC1, has a variance of 12.08, whereas PC2 has only a variance of 0.32. This means that almost all variance is kept in the first principal component. If we divide the variance of the first principal component by the total variance, we see that the first principal component captures 97.4% of the total variance. Note that the variances of the principal components correspond to the two eigenvalues we calculated earlier. Thus, the eigenvalues of the covariance matrix represent the variances of the principal components. When we study the covariance matrix of our transformed data, we see that the covariance between PC1 and PC2 is equal to 0, which means that PC1 and PC2 are completely uncorrelated. We also see that the variance of PC1 and PC2 correspond to the eigenvalues associated to the first and the second eigenvector. Note that the total variance of PC1 and PC2 is about 12.4, which corresponds to the total variance of the original variables. Remember that when we multiplied our centered data by the matrix that includes the eigenvectors as columns, we got the transformed data. This is the same as using the following equation to calculate the principal components that we saw in the previous video, where the weights for the first principal component comes from the first eigenvector with the highest eigenvalue, whereas the weights for the second principal component comes from the second eigenvector. For example, if we would calculate the corresponding score for person number 6, we would multiply the centered blood pressure values of person number 6 by the corresponding weights. By adding these products, we would get the principal component score of 5. Note that we can also use the following equation to calculate, for example, the first principal component, where we replace the variable for the centered data by the variable of the original data minus its corresponding mean. For example, if we would use the original blood pressure values for person number 6, we would subtract the mean from the corresponding systolic and diastolic blood pressures, which would give us the same values as for the centered data. Note that the general aim of using PCA is to reduce the dimensionality in the data. In other words, we like to reduce the number of variables we have. However, so far we have not reduced the number of variables, since we have the same number of principal components as the number of variables we started with. Since the first principal component captures almost all variance, which can be interpreted as it stores almost all information about the two variables, we can simply delete the second principal component because it includes almost no information. As we have seen previously, by using the following equation, we can combine the two variables into just one variable in a way that maximizes the variance of the linear combination. The weights can be interpreted as how much each variable contributes to the principal component. Since the absolute value of the weight for the diastolic blood pressure is higher than that for the systolic blood pressure, PCA put more weight on the diastolic blood pressure when the two variables are combined. Before we end this lecture, we'll see why the first eigenvector points in the same direction as the data. This is our previous eigenvector, and if we extend it by multiplying by, for example, 6, we can draw this vector. Note that this is also an eigenvector of the covariance matrix, since it has the same direction as the eigenvector with the unit length. This is our covariance matrix. Let's take an arbitrary vector with the coordinates -2 and 3. If we would multiply the covariance matrix by this vector, we would get a new vector that has changed direction. We see that the covariance matrix transformed the vector so it now moves in a direction closer to the eigenvector. Note that we here do not plot the full length of the vector since it cannot fit the screen. The importance is its direction. If we multiply the covariance matrix by this new vector, we will get a new vector again. This new vector will have more or less the same direction as the eigenvector. Let's take another example vector with the coordinates 4 and 1. Multiplying the covariance matrix by this arbitrary vector will result in the following vector. We see that the covariance matrix will again rotate this vector so that it has a similar direction as the eigenvector. We can therefore conclude that the values in the covariance matrix rotate vectors towards the eigenvector, which points in a direction where the data has a maximal variance. This was the end of this video about the fundamental math behind PCA. In the next video we'll focus on how to interpret the output from the principal component analysis.